Okay, in part B of organic and biological chemistry, we're going to look at alcohols, aldehydes, and carboxylic acids. Let's get into it. Let's start looking at alcohols. So alcohols contain an OH group. That's the functional group, an oxygen and a hydrogen. And they're one of the most common functional groups that we deal with in organic chemistry. We'll just start off recapping and naming a slightly more complex example, which I've got drawn up here. So in this case here we have an alcohol. Then we're going to, the ending of the name is going to be an anol. We then need to find the longest carbon chain. Now when we find that chain, it always has to contain the alcohol functional group or whatever group it is. So it's the longest chain containing the functional group. And in that case it's 4. So that would be a bute. And finally we have a methyl group, a side chain group coming here, and that's coming off the 3rd carbon. So that would be 3 methyl butanol. So that's how we would go about naming a slightly more complex alcohol. That's actually the alcohol we used in the lab when we made the ester. Next, let's look at the different types of alcohol. So we can, let's firstly do it in the order I've got it here, talk about oxidizing agents. So oxidizing agents are something that we use in organic chemistry to break chemical bonds. We do more on oxidation reduction later in the year. We've done some of that last year. We don't need to worry too much about the detail now. The most common, there's 2 oxidizing agents we're going to use in organic chemistry. The most common is acidified dichromate, which is orange in colour. This was the product I showed you in the lab with the oxidation of different alcohols. And when that reacts, so when it oxidizes something, it turns into chromium ions, which are green. So you get this really distinct orange-green colour change. I probably talked in the lab about how the early breathalyzers used to use that. It forms the chromium ions here. Now, I've just put the oxidation states of these 2 things so that you can see that it was reduced. There was a reduction in oxidation number, therefore it was reduced, therefore it oxidized something else. We covered that in electrochemistry last year, but if you don't remember that, don't stress, we're going to come back to that later in the year, and it won't be crucial for what we're doing with organic chemistry at the moment. So, that's what an oxidizing agent does. That's our common one, how we tell the difference. Primary, secondary and tertiary alcohols is the next thing we need to know about. Now, in a primary alcohol, the carbon that the oxygen is bonded to is only bonded to one other carbon or no other carbons, which also means that there's either 2 or 3 hydrogens on the carbon that the oxygen is bonded to. But easiest to remember, the carbon that the oxygen is bonded to is only bonded to one other carbon. If it's a secondary alcohol, the carbon that the oxygen is bonded to 2 other carbons, and then there's a hydrogen here. If a tertiary alcohol, the carbon that the oxygen is bonded to 3 other carbons. So that's the difference between a primary, a secondary and a tertiary alcohol. Now, when we oxidize these with our dichromate, which I meant to write in, so I'll just really quickly write in. So when we oxidize these with our acidified dichromate, we get some different reactions that we need to look about. Sorry, I'm just filling for time here because I should have probably paused it, but that's okay. So when we oxidize a primary alcohol, we firstly form an aldehyde. So we would get CH3, C and then on this we would get on this carbon here we would get the aldehyde group. So we've gone from our alcohol, we form an aldehyde. This reaction will keep going, and then we will get a carboxylic acid formed. Now, if you ever wonder why you get a alcohol after drinking ethanol, or what we generally call alcohol, it's actually this ethanol that your body doesn't like. It makes you feel sick, it gives you the headache. Your body takes a while to break that down into the carboxylic acid, which is basically vinegar, which your body is able to easily get rid of because it's got this OH group, so it's more soluble than this one that can only dipole with water, and your body can get rid of it. That's sort of extra information. The key thing here, primary alcohol goes to an aldehyde, and I've forgotten to put an E in aldehyde there. Just pick that up. Should be an E in there. Goes to an aldehyde, then it goes to a carboxylic acid. A secondary alcohol, when we oxidize that, we will get a ketone. So in this case, CH3, and then on this middle carbon, the alcohol will get replaced by the double bonded oxygen group, which is the ketone, and we will get the ketone form. So a secondary alcohol gives a ketone, and finally the tertiary alcohol, when it is oxidized, well, it won't oxidize, so we will get no reaction. So that was the one that when I did it in the lab, you saw stayed that orange in colour. We didn't get that colour change. So just quickly recapping that prac, I've just put this photo here. These were our two primary alcohols. This was our secondary alcohol. This was our tertiary alcohol, just so hopefully you remember what we did in the lab when we looked at the oxidation of alcohols. Thank you. Okay, let's look at aldehydes and ketones now. And in general, you're going to see with these functional groups, there's a bit of a pattern of how do we make them, how do we name them, and how do we break them. And this one's sort of going to follow the pattern. And to be honest, we're not going to talk a lot about how we make them because we already know how to make an aldehyde and a ketone because we make those through the oxidation of a primary or secondary alcohol, which we've just covered in the previous slide. So now let's talk about naming them. Got a couple here that we can name. Got our old favourite here. It's an aldehyde, so that we know the ending of the name is anal, or as some people like to say, anal. How many carbons do we have here? 1, 2, 3, 4. And do get into the habit of numbering. It's good practice. 4 carbons, so it's bute, and al. Also commonly known as but-anal. And now let's look at a ketone. So we've got a ketone here. We know the ending of the name is going to be an anione. Now we always number so the functional group has the lowest number. So we wouldn't go 1, 2, 3 because we could go 1, 2. So we always try and give it the lowest possible number. So we would go from that way. 4 carbons again. The anione group is on the second carbon. And I'm going to make a tiny little correction here to the way I did it because I didn't quite leave myself my space. Maybe I should have just written out underneath. So that is going to be a an 2-one, and because it's 4 carbons, it's going to be butane-2-one. So there's naming a couple of slightly more complex ones. Now, with aldehydes and ketones, there's another oxidizing agent we can use, which is Tollens reagent or ammoniacal silver nitrate. It's the one I demonstrated in the lab that made the silver mirror form on the test tube. It's only a mild oxidizing agent, so it will oxidize an aldehyde, but it won't oxidize a carboxylic acid necessarily. So you don't need to know about that. It's really only knowing here about distinguish between an aldehyde and a ketone, which I'll go through in a sec, but it's also a way that you can distinguish between a carboxylic acid, between an alcohol and an aldehyde, because Tollens reagent isn't strong enough to oxidize an alcohol. Now, we'll come back to that later when we look at carbohydrates, in fact. So, if we oxidize an aldehyde under acidic conditions, so we've got lots of hydrogen ions present, we will form the corresponding carboxylic acid, and because it's under acidic conditions, it'll have this hydrogen attached to it. If we oxidize under basic conditions, so in the presence of hydroxide, essentially the hydroxide reacts with the hydrogen on the carboxylic acid you can think of and strips that off to form water. So what we actually form is the carboxylate ion. And finally, a ketone can't be oxidized any further, so we would see no reaction in that case. So that is the oxidation of aldehydes and ketones, and also everything else we need to know about aldehydes and ketones. Let's get into carboxylic acids. So let's learn how to name, make and break carboxylic acids. So I think we already know how to make them through the oxidation of alcohols or aldehydes. So that was easy. Let's look now at naming carboxylic acids. Again, we look for the longest, we look for the longest carbon chain. In this case, 1, 2, 3. Always start where the functional group is. That's the carboxylic acid group, is what we mean by the functional group. So it is hang on a sec, going to need to leave myself a bit of room. You'll see, you often do this when you're naming them. So it is a prop. However, we've got a side chain here that's on the 2 carbon, and it's a CH3 side chain, which is a methyl. So it's 2 methyl prop. And then because it's a carboxylic acid, the ending of the name is anoic, when I spell it right, anoic acid. So put that all together, we get 2-methyl propanoic acid. So now let's look at what happens when we break them. Now, a lot of this is going to be revision of stuff from right through middle school science through to what we would have done last year in chemistry and to what we covered earlier in the year on equilibrium constants. So let's have a look. Firstly, carboxylic acids, as their name sort of implies, are acids. And we know that hopefully we can remember vaguely from somewhere in our past that an acid plus a hydroxide gives us salt plus water, or an acid plus a carbonate gives us salt plus water plus carbon dioxide, and we get a similar reaction with a hydrogen carbonate. It's your classic vinegar and bicarb soda type reactions, or your classic neutralization reactions. So, carboxylic acid plus a hydroxide. This hydrogen here on the carboxylic acid can be donated to the hydroxide. That's what makes an acid. An acid is a hydrogen ion donor, forming water here and leaving us with the carboxylate ion, which is, if you like, a fancy way of saying salt in year 12. So this is a neutralization reaction. We can also get our acid plus carbonate reaction, which gives us again this carboxylate ion plus water plus carbon dioxide. And finally, hydrogen carbonates. Well, hydrogen carbonates are carbonates. They just have one hydrogen attached. They react in the same way as a carbonate. So we get the formation of a carboxylate ion again, plus water, plus carbon dioxide. Next, we just need to talk a little bit about the fact that carboxylic acids are usually weak acids, which basically means they are only partially ionized. So we would have talked previously about weak acids versus strong acids. A strong acid can donate all of its hydrogen ions. A weak acid only donates some. We can also now explain this in terms of equilibrium. Basically, this reaction here where the carboxylic acid donates a hydrogen ion and leaves you with the carboxylate ion only partially goes to completion. So that means that most of it stays as the carboxylic acid, only a small amount forms the products. So we learnt in the equilibrium topic, we can sort of show that with this two-way arrow, and we've got the big arrow pointing towards this side, indicating this is the side that there's much more of the products than the reactants. Or we can use an equilibrium constant. And basically, the equilibrium constant for this reaction would be very much less than 1. I talked about weak acids, I think, when we did the equilibrium constants video. So this is saying that you would have a lot less products than reactants. Remember, an equilibrium constant is a measure of products divided by reactants. It's a little more complex than that, but basically that's what it is. So that's giving us the equilibrium constant here for the reaction and showing that it's less than 1, meaning it's only partially ionised. It's a weak acid. Finally, we need to be able to compare the solubility of a carboxylic acid with a carboxylate ion. Now, obviously, this is the solubility mainly in water. So in water, the carboxylic acid can hydrogen bond to the water. So it's reasonably soluble because they are quite strong interactions, the hydrogen bonding interactions. However, if we have it as an ion, the ion dipole interactions are much stronger than a hydrogen bonding interaction, which makes the carboxylate ion much more soluble in water than the corresponding carboxylic acid. We cover this in quite a bit of detail in Year 11, and if you wanted to go back, there is videos in the Year 11 section, the Year 11 channel if you like, or playlists, whatever it is, on the YouTube channel, and you can see some of that information there in more detail. Okay, that's it for alcohols, aldehydes, ketones, and carboxylic acids. Thanks for listening.